last lecture we saw that if A is in CNN, that is if A is an n by n complex matrix, then for A to be diagonalizable, we need that the algebraic multiplicity is equal to the geometric multiplicity for every eigenvalue of A. What we mean is, that is, if lambda j is an eigenvalue of A with algebraic multiplicity A j, then we must have A j linearly independent eigenvectors corresponding to lambda j. So, depending on the multiplicity of the eigenvalue, we must have that many linearly independent eigenvectors. This is the same as saying that the dimension of the eigenspace W j corresponding to lambda j must be, or it must A j, must be A j. So, we need this condition for diagonalizability, and we have seen that there are matrices for which this condition is not satisfied. This condition is not satisfied and hence not diagonalizable. So, there are matrices for which the condition is not satisfied, that is, the geometric multiplicity will become less than the algebraic multiplicity for some eigenvalues, and hence the matrix fails to be diagonalizable. Therefore, we have this problem that given a matrix A, a priori we do not know whether it is going to be diagonalizable or not. We have to look at the geometric multiplicity and the algebraic multiplicity, that is, we look whether we get enough number of eigenvectors to form a basis for the whole space. Now, we are going to look at a class of matrices. We shall now look at a class of matrices which is a subclass of the entire set of matrices, for which always A m equal to G m for each eigenvalue. So, we are going to look at matrices, a class of matrices. Among this whole world of matrices, there is a class of matrices for which this condition is always satisfied and hence diagonalizable. And this is the first subclass of matrices we look at. What we mean is the following: we have this whole collection of n by n matrices. Inside that, we are going to look at a subclass H n. We will define what H n is, and this subclass H n, you take any matrix A in this subclass H n, it will be diagonalizable, or for which algebraic multiplicity will be equal to geometric multiplicity. So, we will call this subclass H n. We will explain what H n is shortly. So, for that we will look at some preliminary ideas, simple calculations, which will give us the right notational framework to work with. So, let us look at a matrix A which is n by n complex. Then let us denote it as the entries as A, J, K, where J is the row index which goes from 1 to n and K is the column index which goes from 1 to n. So, we have a complex matrix A whose entries are A, J, K. A, J, K denotes the entry in the jth row and the kth column, and it is a complex number. Now, take any vector u in C n, then u is of the form u equal to u 1, u 2, u n, where the u j's are all complex numbers. Now, if u is a vector in C n, then A u, if we multiply the vector by u, the matrix A, that is also a vector in C n, because A is n by n and u is n by 1. So, the product is going to be n by 1. So, it is also going to be a vector in C n. So, if we take a vector in C n, A u is also going to be in C n. So, we can write A u as its first component we will denote by A u 1, second component by A u 2 and so on A u n. Now, how do we get the jth component? A, look at the vector A u, A is obtained by multiplying the matrix A 1 1 A 1 n, A 2 1 A 2 n and so on A n 1 A n n with the vector u 1 u 2 and u n. In order to get the jth component of this product, we have to look at the jth row and multiply it with the vector u 1 u 2 u n. So, we get the jth component of A u to be A j 1 u 1 plus A j 2 u 2 plus etcetera A j n u n, which we will write in summation notation as summation k equal to 1 to n A j k u j. So, the jth component of the product A u was given by A j k u j. Now, consider two vectors x and y in C n. X is x 1 x 2 x n, y is y 1 y 2 y n. Now, applying the above logic, we get A x is a matrix and its component jth component by the above calculation. In this we replace u by x, we get that is equal to k equal to 1 to n A j k x j. That is our A x j. Now, if you look at the inner product of A x with y, by definition that is summation j equal to 1 to n, the jth component of A x multiplied by the jth component of y with the conjugate, because we are dealing with the complex vector space. Now, A x j we have calculated here, and if we substitute that, that becomes j equal to 1 to n summation k equal to 1 to n A j k x k times y j bar. Now, we have two sums, one is on the index j and the other is on the index k, and both are finite sums, and therefore, we can interchange the order of the sum. So, we will take the k sum first and then x, this should be x k, the x k comes out and the remaining all are dependent on j. So, they all go inside as A j k y j bar. We can now write this as summation k equal to 1 to n x k j equal to 1 to n A j k bar y j this quantity bar. we have taken the conjugation twice, and for simple notation we write this as summation j equal to 1 to summation j equal to 1 to n a star k j y j bar, where a star alpha beta is a beta alpha conjugate from the above definition for any alpha beta between 1 and n. And therefore, this becomes, if we now define the matrix A star to be the matrix whose entries are A star alpha beta, which is equal to A beta alpha, then this becomes k equal to 1 to n a k A star y k bar, which is the same thing as the inner product between x and A star y. This is explicitly seeing this computation of A x comma y is equal to x comma A star y. Therefore, what is the conclusion? The conclusion is that if A belongs to C n n, we define A star. How do we obtain as A star? We interchange the row index and the column index and then conjugate it. Interchanging the row index and the column index amounts to transposing the matrix. So, it is A transpose conjugate. So, A star alpha beta is equal to A beta alpha bar. If we now define A star as A transpose bar, then A x comma y is equal to x comma A star y for every x y in C n. This is a very important identity which will be used repeatedly. In particular, if we take everything real, if A belongs to R n, then there is no more conjugation involved. So, A star will be defined as A transpose only. Then we have A x comma y is equal to x comma, in place of A star we have A transpose y for every x y now in R n. These two are important observations for a matrix, very important identity. A x comma y equal to x comma A star y, that is, if we move the A in the inner product from one factor to another factor, it moves as a star. Here A was in the first factor, now we wanted it to move to the second factor, it moved as a star. Similarly, if it has to come back from second to here, it will come back again with a star. Note that A star star is equal to A. Take the matrix, again transpose, and once you transpose and conjugate, again you transpose and conjugate, you get A. So, these two identities are going to be very useful identities for us. So, let us look at some examples. Let us take a very simple matrix which is 1 plus I, 2, 3, which is now in C 2 2. So, it is a 2 by 2 matrix, it is a complex matrix. Now, what is A star in this case? We have to transpose and conjugate. So, this conjugation will make this I, transposition will bring the I here and the conjugation will make it minus I, and the 2 goes there and 3 comes here. So, this is what A star. So, suppose x is a vector x 1, x 2 which is in C 2, then what is A x? A x is 1 plus I 2, 3 into x 1, x 2, which is 1 plus I into x 1 plus I into x 2, 2 x 1 plus 3 x 2. This is what A x is. So, now if we take the inner product of x with y, the inner product is taken by taking the components of the product of the components with the second one coming as a conjugate. So, the first component of A x times the first component of y conjugated plus the second component of A x times the second component of y conjugated. We will make a slight readjustment of this. We will write this as x 1, collect all the x 1 terms, which is 1 plus I into y 1 bar, and x 2 plus an x 1 comes from 2 y 2 bar. Then we have plus x 2 into I y 1 bar plus 3 y 2 bar. This is what A x comma y is. Let us compute A star y. A star y, recall A star is the matrix 1 minus I 2 minus I 3. So, 1 minus I 2 minus I 3. Again let us look at this, 1 minus I 2 and minus I 3 is A star, y is y 1 y 2. So, if we now take this product, this becomes 1 minus I into y 1 plus 2 y 2 minus I into y 1 plus 3 y 2. And therefore, x comma A star y, that is the inner product of x with A star y, will be the first component of x 1 times the conjugate of the first component of A star y, which is 1 plus I into y 1 bar plus 2 into y 2 bar. Similarly, second component of x into the conjugate of the second component of y. Now, compare it with A x comma y, which we got here, and we see that it is the same as A. Thus, A x comma y is equal to x comma A star y for every x y in C n. This is the identity that we have been discussing about. Let us look at another example. Let us take A to be 1 I 2 minus I. Now, in this case, what is A transpose? It is 1 I minus I 2, and A star is the conjugate of the transpose. So, it is 1 I minus I 2. We have to conjugate the A transpose to get A star. So, again what is A x? A x is 1 I minus I 2, that is A, x is x 1, x 2. If you now take the product, I get x 1 plus I x 2 minus I x 1 plus 2 x 2. Now, if I take A x comma y, which is the inner product of A x with y, I have to take the first component of A x, multiply it with the conjugate of the first component of y plus second component of A x multiplied by the conjugate of the second component of y. When we do this product, we rearrange these terms again as before, collect the x 1 terms, I get x 1 into y 1 bar minus I y 2 bar plus x 2 into I y 1 bar plus 2 y 2 bar. Now, let us compute x comma A star y. First of all, what is A star y? A star y is the same as A y, because we observe here that A star is equal to A. A star is equal to the same as A y. So, it is again 1 I minus I 2 into y 1 y 2, which is y 1 plus I y 2 minus I y 1 plus 2 y 2. Now, therefore, if I take x comma a star y, the inner product of x with a star y, I must have x 1 times the first component of, we have to put the first component of a star y with the conjugate. So, it will be y 1 minus I y 2, y 1 bar minus I y 2 bar plus x 2 into the second component of a star y with conjugation I y 1 bar plus 2 y 2 bar, which is precisely what we got here for a x comma y, and therefore, x a x comma y is equal to x comma a star y. In this case, a star is a. Let us look at another example, the real case. Consider the matrix 1, 2, 3, 4. What is A transpose? It is 1, 2, 3, 4. A x is x 1 plus 2 x 2, 3 x 1 plus 4 x 2. A transpose y is x y 1 plus 3 y 2, 2 y 1 plus 4 y 2. And therefore, A x comma y, now we know we do not have any conjugation, because now we are looking for x y in R n. So, if we now take x y in R n all real, then A x comma y is first component of A x into the first component of y plus the second component of A x into the second component of y, which we will rearrange again as before, x 1 into y 1 plus 3 y 2 plus x 2 into 2 y 1 plus 4 y 2. On the other hand, we have x comma A transpose y is equal to x 1 into the first component of A transpose y, which is y 1 plus 3 y 2 plus the second component of x into the second component of A transpose y. You compare these two and we see that these two are equal, and therefore, A x comma y is equal to x comma A transpose y for every x y in R. So, when we have, so let us again summarize with the examples. And so, first A belongs to C and N, we define A star to be transpose the matrix and then conjugate, and then A x comma y is equal to x comma A star y for every x y in C n. A star is called the Hermitian conjugate, is called the Hermitian conjugate of A. Then the second thing we observe is, if A is in R n, then A x comma y is equal to x comma A transpose y for every x y in R. So, now we observed that when A star is equal to A in this example 2 above, particularly if you look at this identity, when A star is equal to A, then we get A x equal to x comma A y, that is we can freely move A from one factor to the other factor without any change. If A star is equal to A, when we move this A to the second factor, it will still move as A only, and that makes things work much nice. We now make a special name for such matrices. So, we now introduce the notion of a Hermitian matrix. A matrix A which is complex and n by n is said to be Hermitian if A star equal to A. So, the conjugate Hermitian conjugate is itself. So, it is self conjugate matrix. So, it is a self conjugate matrix in the sense of Hermitian conjugation. The Hermitian conjugation is transpose conjugate. So, if you transpose and conjugate the matrix, if you get back the original matrix, then it is called a Hermitian matrix. For example, if A equal to 1 I 1, A transpose is 1 I 1, therefore, A star is equal to A transpose conjugate is 1 minus I 1, and this is not equal to A, and therefore, A is not Hermitian. On the other hand, look at this example, A equal to 1 I minus I 1, then A transpose is 1 minus I 1. The rows are written as columns and columns as rows. Therefore, A star which is the conjugate of A transpose is 1 I minus I 1, which is equal to A, and therefore, A is Hermitian. Therefore, A is Hermitian if and only if its star is itself. In particular, when we are dealing with real matrices, conjugation has no effect. A star means is the same as A transpose. So, if A belongs to R n and A transpose equal to A, we say A is real symmetric matrix. Note that a real symmetric matrix can be thought of as a complex Hermitian matrix, because the real numbers can be thought of as complex. So, starring again does not affect, A transpose conjugate will still be A. So, note a real symmetric matrix can be thought of also as a complex Hermitian matrix. Now, suppose A is Hermitian and we denote we say A is Hermitian if A star is A. Therefore, if you look at the diagonal, what does that mean? This means A j k bar, let us use the following notation, correct notation. So, the j kth entry of the starred matrix is obtained by the k jth entry of the original matrix with conjugate. So, in particular, if j equal to k, we get the diagonal entries we get the jth for the jth diagonal entry A j j star must be equal to A j j bar. Now, if A is Hermitian, A j j star is the same as A j j, because A star is equal to A, and therefore, A j j bar is equal to A j j, which says A j j is real. Therefore, for a Hermitian matrix, all the diagonal entries must be real. The diagonal entries of a Hermitian matrix must all be real. The matrix may be complex, but when the matrix has to be Hermitian conjugate, the diagonal entries are forced to be real numbers. So, you cannot have a complex Hermitian matrix with complex diagonal entries. All the diagonal entries must be real. Now, we shall denote by H n the set of all n by n complex Hermitian matrices. So, what is H n? H n is all those matrices in C n n, they are complex Hermitian complex matrices n by n such that A star is equal to E. So, this is the collection of all Hermitian matrices. Now, it is this class of matrices which are having a very nice set of properties as far as the eigenvalues and eigenvectors are concerned, and it is this class that will be very useful in all our computations and answering many of our questions that we raised in the beginning of the course. So, we shall study this class a little bit more closely. So, okay, so first some simple properties of H n of this collection. We shall look at some simple properties of this collection of matrices. First, we have observed that the moment it is Hermitian, so if A belongs to H n, A x comma y must be equal to x comma A y for every x y in C n. Because A star is equal to A, we had A x y is equal to x comma A star y, but since A star is equal to A x comma y must be equal to x comma A y. So, this is the first property which every matrix in H n possesses, that is, in an inner product the factor A can be moved from the first to the second without any change. The second is, as we observed above, if A belongs to H n, then all diagonal entries of A must be real. All diagonal entries of A must be real. Let us now look at the property 1 as in a special situation. So, in 1, if we put x equal to y, we get A x comma x is equal to x comma A x. Y is equal to x. So, A x comma y becomes A x comma x, and x comma A y becomes x comma A x. So, we have we have this simple thing when we put this. So, this is true for every x in C n, y is also taken to be equal to x. So, that becomes for every x in C n. Now, but the right hand side by the inner product rule, inner product of a vector with itself is the conjugate when the order is reversed. So, we have got A x comma x. So, therefore, A x comma x is equal to A x comma x bar. So, a number is equal to its own conjugate means that number must be real. So, that says A x comma x is real for all x in C. So, this is the third important property. Not only the diagonal entries are real, there are many things that are going to become real for a Hermitian matrix. Okay. Not only the diagonal entries are real, we now see that A x comma x is real for all x in C n, whatever x, the x may be complex, A is a complex matrix, only thing we know it is a complex Hermitian matrix. So, there may be many non-diagonal entries which are complex, x could be a highly complex matrix, a vector, and yet if A is Hermitian, A x comma x must be real. All the complexity is gone and everything becomes real. So, A x comma x is real for all x in R n. It is a very important property. So, which we will be using repeatedly. So, we have seen now three properties. This is the first fundamental identity for Hermitian matrices, A x comma y equal to x comma a y for all x y in C n. All diagonal entries must be real and A x comma x must be real for all x in C n. Suppose A and B or I am sorry A and B are Hermitian matrices. Suppose A and B are Hermitian matrices, that is A star equal to A and B star is equal to B, both are Hermitian matrices. Suppose we take two Hermitian matrices and we look at their sum, call that as C. So, let C be equal to A plus B, the sum of these two matrices. Then C transpose is A transpose plus B transpose, because the transpose of a sum is the sum of the transpose. Therefore, C transpose conjugate is A transpose conjugate plus B transpose conjugate. This is C star and this is A star, this is plus B star. That is, the sum of the stars is the star of the sum. So, C star is equal to A star plus B star. In particular, if A and B are Hermitian, this is the same as A plus B, because A and B are Hermitian. So, if A and B are Hermitian, A star is equal to A and B star is equal to B, but A plus B was C. That means, C star is equal to C, that means C is also Hermitian. So, conclusion is A, B are Hermitian implies their sum is also Hermitian. The sum of Hermitian matrices is a Hermitian matrix. However, there is certain, so that is the fourth important property. However, there is a slight problem as far as product scalar multiple on products are concerned. Let us look at a Hermitian matrix and take any complex number C. Then let us define C to be alpha times A, that is the matrix A is multiplied by alpha, which means every entry is multiplied by alpha. So, C transpose is alpha times A transpose and therefore, C transpose conjugate is alpha conjugate A transpose conjugate, that is alpha conjugate A star. Now, therefore, C star is equal to alpha conjugate A star. So, therefore, C is Hermitian if and only if C star is equal to C, if and only if alpha bar A star, that is the C star must be equal to alpha A, if and only if alpha bar A is equal to alpha A, because A star is A. We have assumed that A is in H n. Since A is in H n, A star can be replaced by A. So, C will become Hermitian if and only if alpha bar A equal to alpha A. Now, this is satisfied if A is the 0 matrix. If A is not the 0 matrix, then alpha must be equal to alpha bar if and only if A equal to 0 n cross n or alpha is real. And therefore, if we have a non-zero Hermitian matrix, its scalar multiple is also Hermitian if and only if the scalar is real. So, therefore, A belongs to H n, A not equal to 0 n, then implies alpha A is Hermitian is also in H n if and only if alpha is real. So, this is the scalar multiple of a Hermitian matrix will become Hermitian only if the scalar which is multiplying is real. This is same thing as saying H n, the class of all Hermitian matrices, is a vector space not over the field of complex numbers, but over R, because addition of two Hermitian matrices is Hermitian. So, addition no problem. Scalar multiple, in order that it be close with respect to scalar multiple, we have to take only scalars to be real. So, that is the problem with or the constraint with respect to scalar multiplication. The next property is look at the product of two. So, this is the product. Suppose A is a Hermitian matrix and B is also a Hermitian matrix. Let us define C to be the product, define C to be the product A B. So, we have two Hermitian matrices and we are looking at their product. What is C transpose? It is A B transpose, but A B transpose, the transpose of a product is the product of the transpose in the reverse order, and therefore, C transpose conjugate is B transpose conjugate into A transpose conjugate, and this is C star and this is B star and that is A star, and that is equal to B A, because B and A and B are Hermitian. Since A and B are Hermitian, B star is B and A star is A. Now, therefore, C star is equal to C, that is C will be Hermitian if and only if C star is B A, C is A B, that is if and only if A and B commute. Therefore, that is the next property, product of two Hermitian n by n matrices is again an n by n Hermitian matrix, if and only if the two matrices commute. These are some of the important properties of a the collection of Hermitian matrices. Let us go over them. The first property we had was that we must have a x comma y equal to x comma a y for every x y in C n. Then we must have that all the diagonal entries must be real, then a x comma x is always real, that is the third property. And the fourth property is that the product, the sum of the two Hermitian matrices is Hermitian always, and this should be the fifth property. Then numbering has been a problem. The fifth property that A is Hermitian, then the scalar multiple is again Hermitian if and only if all the scalar is real, and this is the sixth property is about the product, and the fourth and the fifth properties together give us that H n is a vector space over R, it not a vector space over C. It is not a vector space over C. Then the product of two Hermitian matrices is again Hermitian if and only if the two matrices commute. So, now we have these fundamental basic properties of Hermitian matrices, and we again stress that two of the most important properties which we will repeatedly use is the fact that A x comma y equal to x comma a y for all x y, and A x comma x is real for all x. These are all two characteristic properties of Hermitian matrices. A x comma y equal to x comma a y for all x y, and A x comma x is real. So, now we are going to look at this class of matrices which is closed under addition, which is closed under real scalar multiplication, which is not closed under multiplication, because the product of two Hermitian matrices need not be Hermitian matrix. The product becomes Hermitian if and only if the two matrices commute with each other. Commutativity is an important property of matrices which has a lot of things to say about between the two matrices what happens. Okay. The class H n of Hermitian matrices exhibit noise eigen properties. That is the reason why we look at this and deal with these matrices so very often, because as far as these eigen properties, eigen values, eigenvector properties and their structure, they are very nicely built in, which makes them automatically diagonalizable, not only diagonalizable, but nicely diagonalizable. So, in this context, before we get to study the eigen properties of these matrices, we shall introduce certain notations and terminologies. Let us say U is a matrix whose columns are phi 1, phi 2, phi n. So, U is a matrix, therefore, phi j belongs to C n. Each column is an n component vector. So, we have a matrix U whose columns are phi 1, phi 2, phi n, and suppose what does this mean? This means that phi j, phi k are orthogonal to each other and each vector is length 1, which means phi j are orthonormal vectors, that is phi 1, phi 2, phi n are orthonormal vectors. So, a matrix U in which the columns form an orthonormal set of vectors. Then we have U star is transpose conjugate. So, it will be phi 1 star, phi 2 star, phi n star. and when we multiply u star and u, we get phi 1 star, phi 2 star, phi n star, that is u star, into u, u is phi 1, phi 2, phi n. If we now multiply, first we get phi 1 star phi 1, which is 1, because phi 1 star phi 1 is the inner product of phi 1 with phi 1. So, that is 1. Phi 1 star phi 2 is 0, because phi 1 and phi 2 are orthogonal, and we go on getting 0. And in the second row we get phi 2 star phi 1, which is 0 again, because the inner product between phi 2 and phi 1 is 0. Phi 2 star phi 2 is 1, again we get this. So, we see that we get the matrix I n, which means u star is the inverse of u and vice versa. So, therefore, u star u equal to identity, hence u star is equal to u inverse and u is u star inverse. Any matrix which has this property is called a unitary matrix. So, a complex matrix U in CNN is said to be, this is the definition, is said to be a unitary matrix if u star u equal to I, and since u and u star become inverses of each other, this is the same as telling u star, that is u star is equal to u inverse and u star inverse is equal to u. Then we say it is a unitary matrix. We see that if the columns are all orthonormal vectors, then automatically u is an unitary matrix. In the real case, we have to replace, there is no conjugation. So, u star is the same as transpose. So, we define a matrix, let us call it as O, let us use a different symbol, let us put this O belonging to R n is said to be a real orthogonal matrix if O transpose O is equal to identity. That is, O transpose is O inverse and O transpose inverse is equal to O. So, in the real case we have the orthogonal matrix notion, and the complex case we have the unitary matrix notation. The commonality is that if you are in the unitary case, in the complex situation, the columns form an orthonormal set of vectors. In the real case, when you are having orthogonal matrix with the real inner product, the columns form an orthogonal matrix. So, now we are going to look at the eigen properties of H. This is the most convenient class of matrices for which the eigen properties are very nice, and this will form the subject matter for the next lecture.